Hi, Mr. Tarot. In this video, we're going to do 3 examples dealing with the binomial theorem. We're going to have timestamps in the description so you can jump ahead in case you don't need to hear the fundamentals taught. You just need to see a review. You'll also find a link to a video that I did years and years ago when my hair was still brown. You'll also find a link to a website where I have my lessons organized by subject and playlist, so you don't have to go and see, oh my goodness, Mr. Tarou's got, I don't know, 150 videos in his pre-calc playlist, and I need to scroll through all that. It's a little bit easier to find. This is one of the rare occasions I get to teach something that, and feel good about it. I'm actually going to teach you a shortcut. We're going to go through something called the binomial theorem that says when you have a simple binomial of a plus b, where the degree of each of these terms are 1, or the exponents are 1, and our coefficients are 1, at least as an initial, of course, basic formula, raised to the n power, that's going to be the summation, where you have the sigma notation, repeated addition. The summation, where r starts at 0, goes to n, of n over r. This thing's called a binomial coefficient. If you've already studied permutations and combinations, this will look familiar. The binomial coefficient is n choose r. In probabilities, it's choosing a certain number of items out of a certain size population where the order doesn't matter. So we have n factorial, or n over n minus r factorial times r factorial. That times a to the n minus r power times b to the r power. This looks a little bit complicated. We'll get to it here in a moment. I first want to, again, cover the fundamentals. This is going to be useful for the first and second part of our video, or maybe if I wanted to, instead of asking for the first 3 terms of expansion, maybe say find the 7th term. For our third example, though, we're going to be just going straight to the, well, something called Pascal's triangle. So to get the fundamentals out of the way, let me show you a nice pattern here. We have a plus b to the 0, which is 1. We have a plus b to the first, which is a plus b. A plus b squared, which is if you write a plus b times a plus b and distribute together, we have a squared plus 2ab plus b squared. If you then go, hey, what's a plus b to the third? Well, that's not a ridiculous amount of work. You could write this binomial 3 times and distribute it. When you get done, you'll have something that looks like this. A cubed plus 3a squared times b plus 3ab squared plus b cubed. Now, if I'm like, hey, you're enjoying this so much, let's figure out what a plus b to the 4th power is, you're probably going to start looking at me a little bit ugly, because you're like, I do not want to write a plus b 4 times and then just do all that math of distributing and combining like terms. But I could be like, hey, well, you've already figured out what a plus b to the 3rd power is. Just do one more multiplication. Now, you might be going, well, yeah, you can just write the answer because you've memorized it. I mean, you are the teacher, right, Mr. Tarou? Not really. What I'm looking at, and as I expand these out, once you start doing this enough times, you realize there's a bit of a pattern, the binomial theorem pattern formula. This binomial coefficient, this n choose r, for each of the terms, it starts off with, okay, so for coefficients of 1, 3, 3, and 1, we have n is 4, r is 0, n is 4, n is 3, r is 0, n is 3, r is 1, n is 3, r is 2, n is 3, r is 3. And you can work that binomial coefficient formula and work with simplifying those factorials to create these coefficients of 1, 3, 3, and 1. But also what's happening, it's Pascal's triangle, like I said, and these coefficients are created, at least you can see it as you work down one line at a time, through addition. 1 plus 1 is 2. 1 plus 2 is equal to 3. Another 2 plus 1 is equal to 3. And we always start and end with 1. We have 1 plus 3, which is 4, 3 and 3, which is 6, 3 and 1, which is 4. So if I wanted you to write out a plus b to the 5th power, well, the coefficients before you start involving some more complex terms in your binomial. They start off as 1. 1 and 4 is 5. 4 and 6 is 10. Another 6 and 4 is 10. 4 and 1 is 5. And then finally 1. And another pattern that I hope you've seen so far is when you see this a plus b to the 4th power, the exponents for the one or multiple variable factors in your terms, at least, okay, and this is going to be if you have a variable in both the first and second term of your binomial, they're going to add up to be that power. We have a 4, we have a 3 and a 1, which those exponents add up to 4. We have 2 and 2, add to 4, 1 and 3, again add to 4, and finally we have that last power of 4. So, and our first term becomes one of our factors, and that power goes down, 4, 3, 2, 1. That's what's happening through the sigma notation. You first plug in r as 0, then you plug in r as 1, 2, 3, and keep going until you get to n, and ultimately add all those terms up. So a plus b to the 5th is 1, a to the 5th, 5, a to the 5th b, plus 10, a to the 4th b. Nope, messed that up a little bit. 4 and 1, 3 and 2, plus, so a goes a to the 5th, a to the 4th, 3, 2, 1, and no a, or a to the 0. The b goes to a power of 0, 1, 2, 3, 4, 5, and this sigma notation creates all those additions. So that's the pattern, that's the magic, that's what's going on behind our binomial theorem. Let's get this cleaned up and do our first example. So again, it was already up here, but write the first 3 terms of x plus 2 over x squared raised to the 12th power. Now, I do not want to go to basically the 13th line of Pascal's triangle to write out the first 3 terms. And, you know, we need to understand how to use this. So, okay, first of all, you want to write this as 1x plus 2x to the negative 2. I find it easier to write this with our negative exponent to the 12th power. First 3 terms. Okay, so we're going to let r be 0, 1, and 2 with that n value of 12. And work through that binomial coefficient. So I'll do the one that requires the most work. You saw that with the expansion of those initial binomials that our first coefficient, again, we'll have a change a little bit with this factor of 2 or coefficient of 2 on our b term, but this is going to be 1. This is going to be 12, because I should have pointed that out through the expansion as well, but the second term always has the coefficient, before you simplify things, of n. So this is going to come out to be 12. But let's make sure we understand how to simplify with these factorials. Our 12 over 2, that's going to be our n is 12, r is 2, so we're looking at 12 factorial over 12 minus, thinking of the answer, 2 factorial times 2 factorial. Well, that's 12 factorial. 12 minus 2 is 10 times 2 factorial. Well, remember, 12 factorial is 12 times 11 times 10 times 9, 8, 7, 6, 5, 4, 3, 2, 1. And 10 factorial is 10, 9, 8, 7, 6, 5. Oh, wait a minute. 12 factorial over 10 factorial, after you write that expansion out, you're just going to have 12 factorial over 10 factorial is 12 times 11. Everything past 10, 10 times 9, 8, 7, 6, 5, 4, 3, 2, 1, is going to cancel with those common factors in the numerator. So we have, what, 12 times 11 over 2 factorial, or 2 times 1 is 2. For goodness sakes, please do not do 12 times 11 and then divide by 2. No. 12 divided by 2 is equal to 6, and 6 times 11 is, well, 66. our first term is going to have powers that start at 12 and go down. So x to the 12th, 11th, 10th, as r goes from 0, 1, and 2 with that 12 minus r power on the first term of our binomial. And then, I guess we'll just use right again, our second term, include the 2, and include the negative, by the way. If you have a minus, in, if it's like x minus 2x to the negative 2, think of that as plus a negative 2x to the negative 2, and include the negative as you start identifying what a and b are. But here we have 2x to the negative 2 raised to the 0, 2x to the negative 2 raised to the first, and 2x to the negative 2 raised to the second. And then here comes sigma to say add all these terms up, or at least the first 3 terms, when after you let r equal 0, 1, and 2. Our final answer for the expansion of our first 3 terms then is going to be 1x to the 12th power plus, well, this isn't the final answer, but we have 12 times 2. We have an x to the 11th and an x to the negative 2. We have a plus. The 12 choose 2 gave us 66. And we've got a wrong answer in my notes. We've got a 2 squared, which is equal to 4. We have an x to the 10th and an x to the negative 4th, because negative 2 raised to the second power, that's power to power you multiply, that's x to the negative 4th. Okay, so we have x to the 12th plus 12 times 2 is 24. And then when you multiply like bases, you add the exponents. So 11 plus a negative 2 is 9. And now I can't glance in my notes to see this. So we have 66 times 4. Well, 60 times 4 is 240. And 6 times 4 is 24. So we're looking at 262. And then we have x to the 10th times x to the negative 4. Well, again, when you multiply like bases, you subtract those exponents. So we have 262 x to the 6th power. Now, that's not the full expansion of this binomial to the 12th power, but it is the first 3 terms. Let's get on to part B right now. Alrighty then. I was going to clean up the board, but then I remembered that I think I want to use part A, or the first example, to help guide you through this one. And you may see it very quickly, you may not. So scratch work, I think, will help tie it together. Find the term independent of x. Now, I was teaching out of a brand new book the last couple of years, and I had never seen a question that read like this in my previous math books. So this one threw me off a little bit at first. Find the term independent of x. Find the term, like independent in statistics is like, where one event is not affected by another. So a term that's independent of x means the term is going to be the same regardless of what x is. Well, a term that is not going to be affected regardless of what, say if it's an equation you plug in, like that independent variable of x is not going to change, well then that means that term has to be a constant. That term cannot have a variable of x. Okay, so with our binomial theorem, we have the sum of a bunch of terms that we can create by first letting r equal 0, then 1, 2, 3, 4, 5, 6, 7, up to whatever n is. This binomial coefficient is just that, a coefficient. It'll be a constant if there's no x. And then you have a raised to a power, the first term of your binomial raised to a power of n minus r, and the second term of your binomial raised to a power of r. And with our example, right, we're continuing this from the previous problem, so I have to make up a new one. X is in both our first and second term of our binomial that we are expanding. So A is going to have a factor of x, and B is going to have a factor of x, and you can kind of already see what's going on when I get this out of the way. But these are coming together, and there's an interplay of this n minus r and r. When both the first, or A, and B, when both the first and second term of your binomial have factors of x, well, what happened is we simplified it. We had our A being raised to a power of 12, 11, 10, all the way down to 0. Basically our term of B, again, if that's a minus, include that in here. But we have our B going to a power of 0, 1, 2, all the way up to n, or in this case 12. And as we work this out, we could see that when you multiply those like bases, there's a interplay or a sum, right? When you multiply like bases, you add these exponents. We're basically adding n minus r and r to get to our final power, which is applied to the x. Now, you can already see the pattern here, 12, 9, 6. Those should be going down consistently through the rest of this expansion, probably leading to some negative exponents. You could just really count your way down to the term that's not going to have an x in it, at least in terms of the expansion. Maybe. But what if it was a more complex problem, or what if you didn't already do this kind of work? I'm bringing this up to make you realize that, okay, we have here a exponent of 1 and an exponent of negative 12, and you don't really see it with the 1 because we just sort of get this x to the 12th, x to the 11th, and x to the 10th. But you do see it here where we actually have a more interesting exponent of negative 12. It's getting that negative 2, excuse me, that negative 2 is getting basically with the power to power rule, getting multiplied by r. So in terms of what's going on with the exponents, both the first and second term have that base of x. We have an exponent of 1 getting multiplied by n plus that exponent of negative 2 getting multiplied by n minus r. And the sum of those powers, if you are to not have a factor of x, or in your term, that has to be an x to the 0 power, thus being basically just 1 and leaving you with just the coefficient, which is now your constant. Well, n is equal to the power which you're applying to the binomial, so we're really looking at just 12 plus or minus 2 times 12, what? Negative 2 times negative r is positive 2, so, oh, hello, I didn't do that yet, did I? Yeah, no, minus r is equal to 0. Well, now I think I made a mistake. Yes, I did. Whew. Glad I caught that before I kept going. Did you see it? Hey, maybe it's a learning opportunity. This exponent is not what I wrote here as n. It's not 1 times n. It's, where am I looking at? It's 1, exponent of 1 times n minus r. It was a to the n minus r power. So let me fix that. So this power x to the first, this exponent of 1, is getting raised to the power of n minus r. That's why it's going down, because it's n minus r. And then we have that exponent of negative 2 getting raised to, well, first 0, 1, 2. It's getting raised to the r power. So it's negative 2, at least in terms of power to power. When you start bringing these down, it's negative 2 times r. That has to be 0. Okay, now that looks good. And again, n was equal to 12. So we're looking at 12 minus r minus 2r has to be 0. Now we're looking at combining like terms, negative 3r. Subtract the 12 to the other side, negative 12. R is equal to 4. Now, again, with part A already done, 12, 9, 6, 3, 0. It's the fifth term that's independent of r. There's 13 terms in the full expansion. don't be fooled if you have to actually do this, some kind of similar algebra to solve the problem. Don't be fooled when you get r is 4 and say it's the fourth term, because remember, r starts at 0, right? 0, 1, 2, 3, 4. It is the fifth term is independent of x. Part 3 coming up right now. Last example, a little bit different. It doesn't have any algebra in it per se. I don't have any variables in it. It's really more about arithmetic and working with simplifying radicals, but it's still involving that binomial theorem, that expansion of a binomial. We're going to express square root of 2 plus the square root of 3, that quantity raised to the fifth power, in the form of a square root of 3 plus b square root of 2. So basically, when we get done expanding this and combining all of our like terms, we're just going to have a coefficient of some a on the square root of 3, and b on the square root of 2. And we're looking for a full expansion, and this is just a power of 5. So I'm going to quick do a Pascal's triangle. So I have to work out that whole like binomial coefficient for all of the 6 terms we're going to have in the expansion. So here we have a power of 0, 1, 2, 3, 4, and 5. We're going to remember that our first term gets that power of n, and then its exponent on the first term, as I corrected myself in the previous example, is n minus r. So it's going to be 5 minus 0, 5 minus 1, 5 minus 2, and so on and so on. And so we have, if I write neatly, the square root of 2, or which is better to work with in terms of actually doing work with radicals, 2 to the 1/2 power raised to the fifth, and then the fourth, third, second, first, and then finally 0 term with that n minus r increasing. Well, the r starting at 0 increasing by 1 till you get to n. So we get a last power of 0. I'm going to regret doing this as I try and check my work, but let's go ahead and put a minus in there. My notes have a plus, but I didn't do a negative of 2 terms in the previous example. So negative 3 to the 1/2 raised to the 0 power, and then increase that power by 1. Okay, and again, we're adding in those additions that is the result of that sigma notation. Again, the 1, 5, 10, 10, 5, and 1 is working through that binomial coefficient, or the Pascal's triangle, and the powers of A decrease and the powers of B increase, and those constant, the sum of those powers before we start to get to work should all be 5. Okay, so anything is 0 power is 1. We have 2 to the 5/2 power plus 5. We have 1/2 raised to the 4th power. Well, 4 times 1/2 is 2, and 2 squared, right? 2 to the 2nd power is 4. And I think I'm going to go ahead, this negative is to an odd power. It's going to stay negative, so I'm going to write this as minus instead of plus. And 3 to the 1/2 power. Now, here, our negative is getting squared, so it's going to become positive. And we have 1/2 times 2 is 1, so it's going to be just simply 3, not negative 3. Negative times negative is positive. So we have 3 times 10, which is 30. And then we have a times 2 to the 3/2. Now here we have a negative to an odd power, so it's going to come out to be negative. We've got 1/2 of 2 is 1, so 2 to the 1st, which is 2, times 10 is 20. Negative number to an even power is positive. We have 1/2 of 4 is 2, 3 squared is 9, 9 times 5 is 45. And then 2 to the 1/2 power, so I'm just going to go ahead and write that as square root of 2. And negative 2, odd power is negative, so minus. This is to the 0 power, so it's 1, and we have 3 to the 5/2 power. Okay, so what I want to show you here is, of course, we're going to pull these fractional exponents apart, so we have like a whole number, if you will, or non-fractional. Well, everything, it's still a rational number, but we have 2 to the what? 4 over 2 times 2 to the 1 over 2. I don't know if you need to see this broke down quite that much. I hope if you did, this is going to clarify it. When you multiply like bases, you add the exponents, and 4 over 2 plus 1 over 2 is 5 over 2. Well, we have here what? We have a 2 squared, which is 4, square root of 2. We have a negative 20 from 5 times 4, square root of 3. And a little bit of scratch work here. We have 2 raised to the 3/2 power. Well, that's 2 to the 2 over 2 power times 2 to the 1 over 2. 1 plus 2 is 3. That's 2 times 30, which is 60, and square root of 2. A little exercise with your simplifying rational exponents here. We have 3 to the 2 over 2 times 3 to the 1 over 2. That's 2 over 2 plus 1 over 2 is 3 over 2. We have 2 divided by 2 is 1, so we have 3 times 20 is negative 60. Watch, I'm going to change my question, and it's all going to just come out to be 0 or something, fall apart. Which I feel like I made a copy error somewhere. Yes, I did. That was a square root of 3. You know, the funny thing is I did the exact same thing when I made my notes. Okay, my apologies. But at least I caught it. Sometimes I don't always do. 4 and 60 is 64. Let's do this. We've got 40, 100, 105, 109. And for the square root of 3's, turns out they're all negative, because negative number raised to the odd power. We have negative 20, negative 80, negative 89, square root of 3. If you made it all the way in, thank you very much. If you liked the video, the lesson, please hit the like button. I'm Mr. True. Bam! Go to your homework.